Hi, and welcome back to Videos.org. We're now going to speak to Dr. Jonathan Mitchell on his recent paper on extant species and fossil records of birds. So, Dr. Mitchell, could you please explain the paper?
Yeah, so I'm very interested in how species go from one single common ancestor to a wide diversity of different forms and lifestyles. Birds are quite nice because, people go outside, they see pelicans, they see crows, they see hummingbirds, ducks. They all look radically different, but they all came from a single common ancestor that had a single shape to it. It was a thing. It looked probably a lot like a robin and sort of diversified from there into a wider range of forms. So I'm interested in trying to figure out how to measure the rate at which it went from just one simple single organism into a whole array of different living species. And to do that, I used a molecular evolutionary tree generated by some colleagues over in Yale and brought in a lot of fossil data that I went around and measured a bunch of fossil skeletons and a bunch of modern bird skeletons and basically plucked those different measurements onto the evolutionary tree and sort of tried to calculate how quickly things diverged, how quickly birds radiated into the wide array of things we see today.
So you're talking about taking these measurements. What bones did you use from the fossil birds and from the living birds as well?
So I actually used the wing bones and leg bones. So the humerus, the ulna, and they have a bone called the carpetometacarpus, basically just the hand, as well as the femur, the thigh bone, tibia, and the foot bone. These have a lot of information into like flight styles and locomotion. Birds obviously use their wings to fly, and they use their legs to wade in water if they're a heron, or run around on the ground if they're a road runner. So this captures a lot of how they move around in their environment and how they get prey. I couldn't use beak shape, which everyone knows is very important to birds for ecology. And the reason those weren't in there is because fossil birds tend to have smashed heads. There's just no skull really left. And if there is skull there, it's flattened and crushed and disarticulated, which makes measuring that rather hard. The limb bones, though, are round and robust and tend to hold up well to fossilization.
So would this method be able to be used on other species, or is it just for fossil birds?
It could definitely be applied to any group that has phylogeny, an evolutionary tree of living species, as well as a fossil record. Obviously, you'd want to take different measurements for different groups. You can't really measure limb bones on a clam, for instance. For mammals, you might look at teeth. But in all of these situations, you can take measurements on the creature you're interested in, take those same measurements on fossils, stick them onto the evolutionary tree, and kind of look at how the fossils change your picture of what the diversification looked like.
So is this research going to show limitations in previous studies that have been conducted? Are they going to need to go back and incorporate this into their findings?
Well, it's interesting. This is sort of a limitation people have kind of known about for a while, but no one's really had a way to address. So there's this whole big thing about how quickly creatures radiate. One of the models is what's called an early burst. It's like an explosion of evolutionary forms. You have one common ancestor, and then you quickly radiate to fill out a whole bunch of different regions, a whole bunch of different life histories and styles of ecologies and whatnot. That's one model, and it turns out that people have done mathematical simulations, and it's really, really hard to find a signal of that really rapid early radiation if all you have are living species. So people have done a lot of studies showing that there's not much evidence for an early radiation like that, but they've always caveated it with the fact that we don't have very good statistical ability to estimate it. What I've shown is that when you include fossils, you do start to see more evidence for it. And perhaps more importantly, rather than just taking one model and fitting it and assuming that the parameters you get out of it are the true values, it's, I think, more useful to take a whole bunch of models, fit them, and look at the different parameters and different metrics of statistical support that can paint a more complete picture of the radiation. So one of the things in the paper is the fact that if you had one of these classic burst style radiations, you wouldn't expect the amazing recent divergences of things like Darwin's finches. Because under that very simple model, the rates are very slow in the recent, and you don't get the amazing diversity of finches on the Galapagos. On the other hand, if you use the kind of alternative that people use, this random walk model, you expect to see something in a really old group like ducks. Ducks have been around for forever. They're a very old group of birds. You'd expect to see a huge array of form in them, but you don't. Ducks look like ducks. They've more or less been ducks for a long time. You don't have hummingbird ducks. So there's sort of two contrasting things there. There definitely was an early burst early on, but that let them generate a whole lot of different life strategies. So you have things like ducks that are different from things like songbirds. But at the same time, the rates haven't declined. They haven't gone away like most of the models previously used have supposed, because you still get rapid radiations of things like finches on the Galapagos or honey creepers in the Hawaiian Islands. So I think the paper highlights a lot of things that have been known, but manages to put more firm numbers on them by bringing fossils into the matter. And I think the biggest contribution is the looking at these models not as a strict, this is how it was, but instead more of a general, these all summarize different aspects of how we get the huge diversity of form we see today.
That's really interesting. I really like the idea of hummingbird ducks.
Yeah, that would be adorable.
Yeah. And so what's next for you personally then with this research?
Well, I'm now at the University of Michigan. I'm working in Dan Roboski's lab on better methods for calculating these sorts of high rates of evolution. So I've been doing a lot of stuff recently about putting birds in the kind of broader context. Birds are just fancy looking dinosaurs. So you can take the evolutionary tree of birds and the evolutionary tree of dinosaurs, put them together, and you get one long history of how these things evolved over time, but on a much longer time scale. Instead of having 100 million years of bird history, you have 250 million years of dinosaur history. You can look at how rates have changed in response to various, global phenomena. And the other thing I'm really interested in is finding better ways to bring fossils into this. One big problem is that fossils, whether you end up in the fossil record or not is not random, right? So some things are more likely to be fossilized than others. If you are a small creature with no bones and you live on one spot on planet Earth, you're probably not going to be fossilized. On the other hand, if you're big and have solid bones and live everywhere, the chance that you end up in the fossil record is very good. So there's this sort of bias in what forms you see in the fossil record and what forms may have existed at any particular time. So I'm doing a lot with working on correcting that and exploring what that can tell us about, how much diversity there really was in, say, the Jurassic period.
That's really interesting. And thank you so much. We're going to put a link to the paper below this interview. And Thank you again for joining us.
Thank you for having me.
Thank you. Bye.